Everybody, welcome back to Codeforces Gyms. It's been a while, but today we are back with the segment tree. As you may remember, a couple of days ago we had D1 round in which I did not perform particularly well, in particular because I decided not to implement a very basic uh, segment tree for problem B and went with SQRT decomposition. Now that was a pretty dumb decision. Looking back at it, but at the moment I didn't know. Um, in particular, like one of the reasons why I decided, because I think that I was introduced to segment tree in wrong way. So when I was introduced to the segment tree, I've been like 1500 in Codeforces. So, and this kind of thing was far out of my reach. So like whatever person was teaching me then taught me about there is a segment tree that can like compute the sum of numbers on the segment and change one element. And oh, by the way, it also generalized nicely to 100 different other problems, right? So I feel like it's bad. It's bad to introduce segment tree like that. And because of that, like I was kind of scared of that data structure for a really long time, despite having several moments in my life when I kind of was directly practicing it. I still kind of did not understand it completely, like especially the lazy part. But I believe that now I overcome the difficulty. Um, and I hope that I will teach you better than I was taught some time ago. So let me pull some demonstration. And we won't start with a segment tree. We'll start with something different. And we'll start with the following problem. Suppose we have an array. We'll talk about range queries in general, okay? I feel like it's much more important to understand what's going on in the general setting than to understand only segment tree, right? We have some array. Suppose that we have some range queries. And if you want to find, there are many like different things that you may want to find on range. Range is some subsegment of our array, right? From AL to AR. So what are the common functions that you can ask for? You can try to find sum on the subsegment. You can try to find minimum. You can try to find maximum. You can try to find several more different things, right? Now, one of these is very easy. And this is exactly the sum function. And if you look at the problems in our gyms that I will cover later, actually, let me clear this temporarily. So, like here, we actually have that problem. Problem D asks for range sum queries, but it does not ask anything about updates, neither point updates nor range updates. So this kind of thing is when you can get away easily, right? You can just compute prefix sums and answer queries. Let me show exactly what I mean by that. So suppose we have range sum queries, right? Let me compute array of prefix sums. So first element will be A0. Actually, first element will be 0 just for the purposes of, just for convenience, okay? Second element will be A0, third element will be A0 plus A1, so on. And the last element will be the sum from A0 all the way up to AN minus 1. Clearly, you can compute this in linear time, right? The only thing that you have to be careful about is whether or not you want to include 0, and you don't want any integer overflows, so you can either log int 64t or just use long, right? In this way, you'll avoid any troubles. And prefix sums are that so common that STL actually has a function for them algorithm. For them, it's called partial sum. And there are several ways in which you can reflect these kind of troubles with including and excluding 0, and what is the result type that you actually want to do. But you can see these details in my code that I will show you later when we'll talk about implementation. So suppose you know prefix sums. Now there is one very simple equation that explains why prefix sums are so valuable. This equation is the following. So subsegment from L to R is subsegment from 0 to R minus half open interval from 0 to R, L, right? And if you don't want to think about these half open intervals, you can always write L minus 1 inclusive. So each segment can be represented as a difference of two segments starting at 0. And this part about starting at 0 is pretty important because it means that we can represent any subsegment, right, as a difference of two segments of a very special kind. All this, there are at most, there are actually like n segments of this time, potentially n plus 1 if you count like 0, 0. But either way, there is a linear number of such segments, right? And because of that, and because we already computed all of them in our prefix sums, we can answer our queries pretty easily. If you want to answer such query, the sum on this subsegment will be just prefix sum of R. Sum at this subsegment will be prefix sum at L minus 1. Keep in mind that it's L and R are 1 based here. So this way, L minus 1 is actually defined correctly. The correct index, if L is equal to 1, then you get so this element, which means that you do not subtract anything here, which is exactly what you want. So these are 1 based, 1 based. And I believe that pretty much everyone is familiar with prefix sums. So it should not scare you, right? So far, so easy. But what are the problems when we substitute sum for something like mean? So we already can solve sum, right? We already solved the sum case. But what about mean case? Well, if you're not familiar with that kind of problem, your initial reaction may be the following. Oh, like sum is actually some way to combine numbers, right? We combine a bunch of numbers together. So what and minimum is actually the same thing, right? It combines two numbers together. What if we just take this, shrink them a little, and try to fit the minimum in. So what if we take minimum of prefix minimums, right? So you take prefix minimums here and all the way up to here. And I think that like half of you will be already screaming that, no, you can't do it. And you'll be right, but it's important to understand like exactly what kind of problems do we face in order to solve them. Often I find that like the reason why I couldn't solve problem is because I did not realize what was the issue with a naive approach, right? So it's important to think about stupid things and understand what's the problem with them, like how can we improve? This is actually how new algorithms are born, because you're not satisfied with something simple and you build on top of it. And we'll try to build here. Now, so far so good, right? We substituted one combiner for the other, right? One way to combine numbers for the other way to combine numbers. But what actually happens to this segment equality? What does it mean to subtract one minimum from another? If you just subtract minimums, it doesn't look right. Because when you were subtracting sums, it felt kind of natural. Like you counted some numbers that have smaller index that you should count, and then you subtract them. But what happens here? It's not clear. This is completely unclear. What does it mean to subtract minimums? If you just subtract numbers, you obviously end up with the wrong answer, right? We can show it straight away. Let me actually clear some more space for our needs. So I'll put this condition here. And let's take a look at some examples. I know. So suppose that our array is something like 1, 2, 3, right? As simple as it gets. And we constructed our prefix minimums, which are of course 0, 1, 1, 1. And you can already see that a lot of information about these numbers got lost. Like we have no way of determining whether this number was 3 or 4. So this is actually like already a visual sign that something went wrong. Minimum discards part of information. Well, some also discards part of information, but because we have a lot of them, we can restore it. But here we can't. Like if somebody asks us what is the minimum on this subsegment, which corresponds to 3 in 1-based indices, using this approach, we will happily answer like, oh, it's 1 minus 1, it's 0, right? Even if we are like not that, if we don't subtract, but just take any other combiner, there's still no way you can get from two equal entries. You can't restore this. Whatever, I can put any value here, your prefix minimums will look exactly the same. So they clearly won't work. Now that we figured out what is the problem, let's actually talk about the solution. Before I describe the solution, let's quickly reduce the maximum case to the minimum case. So what if you suppose that somebody gave you a black box that can solve RMQ problem. And RMQ stands for range minimum query. So essentially one of the major problems that we'll solve today is called range minimum query. This is exactly about like what is the minimum on some range. It's suppose that somebody gave you that box. How can you use it to solve max problem? Well, turns out everything's pretty easy, right? If you change your array to negative, like you take negative of each number, then your maximum becomes your minimum. You can find it and then change back to positive numbers. So these two are essentially equivalent. If you can't solve one of them, you can solve the other one. So let's put a check mark here on maximum, because as soon as we solve minimum, we'll be able to solve maximum as well. How actually what are the ways to implement that black box that solves error queue problem? We can get rid of this and we can get rid of this. Because like we already figured out that prefix minimums won't help us here because they discard some information. And one of the things it showed us is that we can't get away storing information only about segments of the form 0 to R, right? So we'll have to store other segments. What segments can we store? There are multiple valid answers. Each of them leads to a different approach. If you watched our previous video about LCA, you may be familiar already with something called sparse table. Right? So a sparse table will answer range minimum queries in constant time, pretty much like prefix sums answered range sum queries, right? But before we delve into some advanced data structures, let's actually understand like why finding minimum in a brute force way is bad. So, I mean, you can always just loop through this interval. If the intervals are small on average, then you're fine, right? But how small exactly they should be? Like, literally 10 minutes ago, I was solving a problem that did not require any range minimum queries data structure because in my problem n was up to 5,000. And I had at most 5,000 queries. So if you have that many queries and not all that long array, well, you can simply find a minimum explicitly on that interval, looping over it, right? Or you can make use of std min element from like STL algorithm. We'll cover it a bit later when we talk about implementation of these problems. But this is exactly what I used like in problem A for that contest. And actually it had even lower constraints. It was like 1K and 1K. If you have that low constraints, you can answer queries in linear time, just looping over the interval. And the time is linear because like if somebody repeatedly asks you queries of the form 0, actually 1 to n, right? Then you can't get away with less than linear number of operations if you loop over that interval, right? So in the worst case, one query can take up to linear number of operations. If there are m queries, then your total complexity gets O of nm, right? But if both of them are like up to 5,000, it actually means that you make around 25 million operations, which is completely fine. Also because you just have like nested for loops, compilers can optimize it pretty decently. So this literally means like 30 milliseconds, something around this lines, on this lines. So if you have like 5,000, potentially even 10,000, you are still most probably fine with naive or error queue, right? And the actual problems start when your n is bigger, and it can be much bigger. Like some typical constraints say that you have 10 to the fifth is the length of the array, and you have up to 10 to the fifth queries. If you now think about this solution, it clearly won't work because it's 10 to the 10th, it's around 10 seconds in the best case scenario. So yeah, most likely it won't work. unless from some like mysterious sources you know that your segments are short on average. And sometimes you actually do know that they are short on average. But such problems are not particularly frequent on Codeforces. So, how can we answer this quicker? I already announced that we can use a sparse table and it will answer queries in constant time. And it also can be used to solve some other important problems like LCA. What it actually means to have a sparse table. Let me move some around a bit just to clear some more space. So we already talked about having segments from 0 to R is not enough. It won't work. And obviously they can't store segments from L to R for all possible values of R and L and R, right? Because there's quadratic number of them, and like potentially if n is small, right? If n is 1000, but for example, m is huge, m can be up to 10 to the 7, to the power of 7, right? In this case, like native RMQ, when you loop over segment won't work. But you can store quadratic number of segments. You can pre-compute maximum or minimum or whatever you want on every segment and then just answer, right? So sometimes when constraints are strange, we can get away with that, like just pre-compute answer to every query because there are not all that many of them, right? You can afford storing 1 million entries. It's perfectly fine with standard memory limits. But if n is huge, even when m is small, like if both of them are up to 10 to the fifth, this won't work because it just uses too much memory. So we need to store some special segments. And one way, like the simplest kind of special numbers in programming are the powers of 2. So one way you can get around is to store this kind of segments. So this is half open interval from L to L plus to the power of K. And you store this kind of segments for all values of L and for all values of K. You can get away with it because K is up to log n. So your total memory usage will be n log n. So you can pre-compute the minimum on every such segment. But you may say, like, wait a minute, like, these segments are pretty long. How do we pre-compute the minimum on them? We can't do it naively because like this value is even higher than our number of queries. So we're actually faced with a range minimum query with even higher number of queries. Okay. We need some efficient way to pre-compute these. And there is a simple way. Because of the special structure, these segments are kind of defined recursively. So suppose I know all such segments with some k, and I want to find with k plus 1. And I can again use some sort of segment decomposition. I just slice into 2 halves, right? Let me finish writing this down and we'll discuss what it actually means. So, like this segment, what is this segment? So we have, and actually it takes a lot of space. Let me, we'll clear some things up. So I think you remember the constraints by now. We can move it here. We can move this thing here. And we can move this thing. Can we please move that thing? Somewhere out here. Okay. Let me grab that segment. Decomposition. Okay. So what we actually have, we have like a pretty long array, and we want to find the answer for that subarray, right? For example, it can be of length 16, right? What we do is we go to the previous layer and we ask it, like, what is the answer on the first half? What is the answer on the second half? In this particular case, answer is minimum. So we can just combine them with taking minimum of 2, right? Does not sound complicated so far. So this decomposition allows you to compute minimum on each such subsegment, like in constant time, right? Because you just make 2 queries to the previous layer, to k, which is 1 smaller. And for k equal to 0, these intervals correspond to a single element of the array. So because of that, you can build sparse table in linear arithmetic time, so that's n log n. It takes n log n space, and it can answer queries in constant time. So let's actually talk about it. How does it answer? When some query comes in, it may not be of the perfect length. It may be of the length like 14, and we don't have such segments. But what we do have is a segment like this, which starts at the same location as the start of that segment and is of length 8. And we also have a segment of length 8 that ends in the same location as our query ends. And we can see that together they cover the entire subsegment, right? So no matter where the minimum is in this subsegment, it will be either here, right, or here, or even in the both of them. And because of that, when we take minimum of these two, we'll definitely find minimum on this array, on this subsegment. This is pretty nice property. So you just have to make 2 queries to your data structure. Each of them is like 1 random memory access. You go to the correct k, and you can find k in pretty much constant time if you use some call to library functions, or maybe you use like built-in count leading zeros, something like that. We'll see the details when we talk about implementation. But the important thing is that you just make 2 random memory accesses, so the total complexity of your query is constant. And sometimes it's important to have constant complexity. For example, when number of queries is very large. So you may, if you know something about segment trees, you may know that you may think that segment tree can solve any range query problem. Like no matter whether it's min, max, sum, min, and max at the same time, no matter whether there are updates or no point updates, range updates, you can simply say, oh no, like segment tree takes care of all of it. But it has a cost. Like you may think that logarithmic cost is pretty low, but sometimes it's not. For example, in the gym that we'll cover problems from it just a tiny bit later. We'll have one problem where we have n up to 10 to the fifth, but m is up to 10 to the seventh, right? And logarithm is small, but it's still not constant. So because of that, like m log n solution does not work. Because segment tree has some constant, right? Number of queries is ridiculously large. Like because of that constraint, they even don't give you like explicit input. They give a generator which you can use to get the input. But such problems, you may sometimes see such problems. And it means that they do not require segment tree. They require something that is truly constant. And one of such things is sparse table. So if you use a sparse table, instead of m log n, you'll get m plus n log n. And both of these are perfectly fine, but not m log n. So yeah, sometimes you have to use sparse table. Let me actually. So we still use the idea of like decomposition of the segment into like small number of simpler segments. But here we used a segments of a special form of length that is power of 2. And pretty much everything that we can do if we want a constant number of segments. But sometimes, like most of the times, we are okay with logarithmic number of segments. And that's exactly what we'll talk about next. So let me clear this all up. So we already can solve range minimum queries in like constant time with n log n build time. Like n log n memory usage is a bit concerning, but not much. Like minimum usually fits in the same data type. It usually always fits. Or like some. So you're missing like how do we answer some queries? Well, you can still use sparse table to answer some queries, but like, why would you want it? We already talked about it. Range sum queries, you can just use prefix sums. And like, it may look like the end of the story. So for minimum, you can use sparse table, which answers in constant time. So even better than segment tree, which has logarithmic complexity. For sum, you use prefix sums. But now the other game changer comes into play. And this is nothing but update queries. And update queries are pretty evil. So we have update queries. I mean, they look evil. You already can tell that they look evil. Now, there are different kinds of update queries. Let's first talk about point updates. So point update, they update one element. For example, somebody tells you like, okay, first I will ask you some or minimum queries, and then I will ask you to change some of the elements. For example, I may ask you to assign the value of x to ai, right? And then I will ask you about sums again. And clearly our data structures do not work well. They are pretty static, right? Static. Once you compute prefix sums, if one number changes, it means that your entire, like all prefix sums since that point are wrong. If you pre-computed sparse table, it means like every segment that contains that point is wrong. And it's pretty much every segment. If you have it like in the middle, then only like this part of the segments will survive. So there's no way to fix it. But there are ways to use like different data structure. And that's why we need segment trees. If we have bus update and queries, right, then we need segment trees. Now, let me actually take some example of a segment tree and an array. So let's say I have some array that looks something like 2, 7, 3, 1, 8, 4, 5, 6. And these numbers do not need to be unique. I just made them unique to make it easy to track what number corresponds to each subsegment. Now, segment tree also uses the idea of decomposition into segments, but it uses a linear number of segments. Actually, that's incorrect. It uses, wait, yes, it uses a linear number of segments, and every segment can be represented as a logarithmic number of such segments. And it does a pretty simple thing. It just splits your segment into two halves. So here you will get 2, 7, 3, 1. That bracket is way larger than it needs to be. So that's first half. And the other half will be 8, 4, 5, 6. And then it does it the same thing again. So we'll have 2, 7. Here we'll have 3, 1. Here we have 8, 4, and 5, 6. And then we have just singular elements. So 2. You know what? Yeah, okay, I will write it. I will write it just to make it as explicit as possible. I have 3 and 1 here. We have 8 and 4 here. And we have 5 and 6 here. Now, it may look like a lot of segments for something of length 8, right? We actually used, if you count carefully, and you also have to count that subsegment, we used 15 segments, which is almost two times as much as the length of the initial array. But it's okay. It will still be linear, because on the last layer we have n segments. Here we have n over 2 segments. Here we have n over 4 segments. And when you sum up this geometric progression, you end up with 2n, right? So usually in implementation, you allocate memory for 4n nodes, but this detail we'll talk about later. Why is this actually good? This is good because every segment that somebody asks you decomposes nicely in its most logarithmic number of segments. For example, let's assume somebody asked, what is the minimum on that query? So this node of the segment tree, it says, I don't know, that's not my segment, go ask somebody else. But it does not just says it, it says who do you need to ask, right? It goes like, well, I will ask my right child about that subsegment. Now I'll ask my left child about that subsegment. Left child says, I don't know, I will ask my children. And so says, I will ask this one. And same way this asks this, goes here and here. And as you can see, like we ended up with 3 segments that know what they're doing. These segments are their segments, so they happily tell the answer. This says 1 is my answer. This says 5. This says 4. Now this, it's not his segment, but his child told him that 5 is the correct answer, so it answers back to note, right? Let me make sure I write 4 properly. So now this segment does not know any of the answers like itself, but his children told him that answers are 4 and 5. So it will take minimum and answer minimum to its parent. This will answer 1, and the entire segment tree will answer 1 to you, because it took minimum of that 1 and that 4. And you may be wondering, like, why it looks like a lot of work for a segment of 5 elements. We asked like 7 segments, right? Actually, like this number is logarithmic, but you may wonder why. And the way you can figure it out, if you look at the unfinished segments, so incomplete subsegments that don't know their answer on each layer, I claim that you will have at most 2 such segments. Because after the initial split, any segment that can end up here will be some suffix. This suffix either won't touch the first half, or it will completely contain the second half. If it completely contains the second half, then on the next layer he will get the answer and it won't go any deeper. If it does not contain, if it's completely in the second half, then it simply won't ask anything of that child. So since that level, we have at most 2 incomplete segments on each layer. And because there is a logarithmic number of layers, we have at most 2 log n incomplete subsegments. And we also have, because of that, like because every complete subsegment is a child of some incomplete, we have also at most like not very strict bound as 4n complete subsegment, 4 log n complete subsegments. So overall, we have logarithmic numbers of segments. And if the tree is like not 8 elements, but 10 to the 16th elements, like 2 to the 16th, then like querying 16 nodes, or even like querying 64 nodes, which is 4 log n, it's kind of faster than just brute forcing that. You can already see. Like, this is actually like 65,000, and you can get away asking like just 65 nodes. So we already have a major advantage in terms of number of segments that we ask. But how do we actually update? Suppose that I want to change this value. Actually, like, if you look at this, you may think that, wait, like, I can clearly see that each layer has, like, stores the entire array. So how on earth is memory usage linear? Now, the truth is that each layer does not store the entire array. They only store like what they will be asked about, which is minimum in our case. So there's nothing here but minimums. Let's actually fill minimums in. So when we build segment tree, we only initialize this layer. And then we say like, this number only, this segment only needs to know the minimum on it. Right? Let me actually make them not segments, but actual values, so that it makes more sense. So we only store values that will be queried for. There are no segments. So then we start building it from bottom to upwards, right? So the minimum here is 2, minimum here is 1, minimum here is 4, the minimum here is 5, 1, 4, 1. Now you can see like why memory usage is linear. Like because we only store one value or maybe two values or maybe like 4 values if we have pretty complicated segment tree, but we only store like constant number of constant amount of information on each layer, on each segment. But what if somebody comes in and says like, oh, can you please change the sort element? We go to that element and they say like, no, actually, let's say they wanted to change fourth element. And it's like, change it to 11, please. We say, okay, let me recompute the minimum on this path. And this path contains logarithmic number of nodes because its depth is logarithmic. Here we say, oh, new minimum is 3, new minimum here is 2, new minimum here is 2. So we only changed logarithmic number of values in our segment tree when processing point updates. So if you have only point updates, you can get away with just this. And this kind of structure is typically represented with an array because there's a smart way to index. The smart way to index is as follows. You can say that the index of this element is 1, 2, 3, 4, 5, 6, 7, etc. So because of that, left child has always double the ID of the parent in right child is always like multiplied by 2, add 1, which is typically represented like bitwise shift 1 or 1. Now let me make this ones like visible. This is what you can typically see in the implementation. So this way, the entire tree, you can get away without representing a tree, and therefore without storing all these pointers and without following these pointers, because following a pointer is actually slower than just making a random access. So like if you know the specific index memory, so you can store the entire segment tree as an array. But that was like update queries, point update queries. And point update is like pretty important part of that that word. Point updates are actually like pretty cheap, right? You just update that segment. You update all the nodes, and you you have all the updated information stored in your tree. So both get minimum and update element take logarithmic time. But what if I told you that I'm not satisfied with point updates and I want segment updates? For example, what if I want, so we'll talk about range updates next. Suppose that I want to change like this entire segment. I just want to assign a value of 11 to it. or maybe I want to add value of 11. So I just want to change the entire segment in some way. Now, you clearly don't want to make this point update for each element because it's too much work. What if somebody comes in and asks you to change half of your tree? You don't want to change this because it's a lot of work. What you can do instead is you can be lazy. So you see this query and you think, well, I don't want to update like everything to 11. What if I just say like, this segment is actually this vertex. What if I just change this to 11? Right? This segment is this vertex, so I will just change this to 11, and here I will change this explicitly. Right? And we already told that every segment decomposes into logarithmic number of segments, and also that this part of the tree, like all values that are on the path from root to this decomposition, it's entire, everything that is like red or on the red path, there's logarithmic number of such nodes. So we can update that part explicitly, but this way, like part of the information remains wrong. So we just lazy updated the segment tree, lazily, right? But what if somebody asks about actually the value of this number, right? Then we'll have to do what's called push. We'll have to explicitly make this update. We'll just say, okay, like I can no longer pretend that I don't have to change my subtree. I will push a new value to my children. Okay, and then they will deal with it. So it's no longer delayed update, right? It's like real update. This value has changed forever now. But its children may not experience push immediately. So if somebody asked for that specific vertex, then this will remain unpushed. So it will store lazy update here. And you will make like each push costs a constant time. You just push to both children and then they deal with it. And because we already analyzed complexity of like how do children work, we don't push we do constant amount of work per vertex that we visit, per node that we visit. And we only visit logarithmic number of nodes in any operation. So the overall complexity stays unchanged if you do these lazy updates. And I used a different color here to denote these updates, these delayed updates. And this is exactly what you will use in the implementation. You will have array tree that stores information that you're interested in, and array lazy that actually stores like these delayed updates. So that's it. And this lazy segment tree is exactly what we needed last div 2 rounds. And I got away implementing SQRT decomposition because I just was scared of segment tree. I did not want to make it, to implement it at the time. And it was a colossal mistake. Because like today I actually decided to implement everything nicely. I didn't implement the most generic version because it's pretty hard to implement generic version of a segment tree. But what I implemented ended up being really short compared to my SQRT decomposition. Like my SQRT decomposition from contest was 200 lines, and lazy segment tree, I got away with 98 lines. And this includes like all sync with the false, like fast EO, reopening the input files because these problems are all. So actually like segment tree itself was pretty short, and I don't know why I did not use it. I will definitely use it the next time when I need some sort of like range updates, data structure. And you don't care about what operation is here. You can store minimum, you can store sum, you can store maximum, you can start many different things in the nodes of a segment tree. The only thing you have to think about is like how to update and how to push, delete updates. If you know how to do these two operations, then you can support any sort of combiner, any sort of like operations that combine several numbers together in your segment tree. So it effectively answers the question about range minimum queries. Now you are capable of making range updates in logarithmic time and range queries in logarithmic time. You may think that, well, that's it. That's it. Like, I can do everything now. And strictly speaking, it's not exactly true. There's one more data structure that comes into play when we talk about range queries. Let's talk about it now. So we can get rid of our segment tree. Okay. We won't even have, we won't have anything. Okay. And what I mean by that is that let's start with an empty array. Like, so far, we only talked about situations when length of the array is constant. But what if it's not? What if the length of your array can change? Our data structures don't handle this good. They can't. They simply can't. They assume that each element has its own fixed position. In segment tree, it determines the entire path. So if the position of some element changes, then you have to recompute all this path of logarithmic number vertices. But if you're like, for example, let's say that we insert elements. So we'll have operation insert at some index I, the value x. Okay. What it means, like for example, suppose that I want to insert 5 into my array on position 0. So my array will become just 5. Okay. And let's say that then I want to insert before 5. You know, as long as the array is not huge, you can do it, potentially you can do something about it. But then when I say like, oh, hey, I want to insert another element at the beginning of our array, and you can see that the position of all elements change when you insert at the beginning. So you have to recompute the path from 3 to the root and from 5 to the root, and you also need to add path from 2 to the root. And just something that you can't handle with segment trees. Well, actually you can, but like, I believe there are some strange versions of segment tree when you can do more than I described. But it's not practical to think about it in this way. If you want to insert elements like anywhere in your array, in your data structure, then what you actually want, like suppose I want to insert 4 here. What you actually want is some way to split your data structure into 2 halves, left and right half. And then you want to insert your new element here, and then you want to merge. You want 2 operations, actually, to be able to insert like anywhere in your data structure. instead of like thinking about it as a segment tree, you want to have two operations which are split by index and merge. Of like left and right parts. Here you will have left and right parts come out of the split operation. Now the data structure that implements this split and merge is called a tree. And you can see that it has elements of both tree and heap in it. And there is a very simple reason for it. So tree actually stores pairs, which are sometimes called key and priority, but more often they just called X and Y. And the point is that it's a binary search tree on X. For example, we have something like 4 here, and priority is 10. And here we have something like 2, and something here we have 6 and something, here we have like, I don't know, 1, 3, and it needs not to be complete, so we may skip like 5 here and just write 7. But on the second element, it's a heap, so it has max elements on top, and then elements get smaller. Something like that is a valid tree. It's BST on the first key, on the first element, and it's heap on the second element. And because of that, it can do amazing things. One of the things it can do is it can split based on some index. If you store the subtree size at each node, for example, here it's 1, 3, 6 to 1. Suppose you want to split at index 3, and you know that you actually want like something like that. This will be left, this will be right. And you can do it. Like this split will be along some edge actually. But maybe it will be like something like that when the index is 2. Well, you can reconstruct it. You can put this as the left child of this. It was originally on the left, so its key will be smaller, so it will remain BST. And its priority was lower because it was lower, so it will remain heap. So you can split trees. And more or less in the same way you can merge them together. And you will understand more what we're talking about when we look at the implementation. Actually, because this video is getting a bit long, we'll talk about implementation in the next part. So this video will remain mostly theoretical. And then I'll talk about implementation in a separate video. They will come out like one after another, so you don't have to worry about it. I just want to split them. The same way I split trees. So because you can split, you can essentially like split on index and then insert. And then you just create a new tree and then you merge these 3 trees together. So you split, you have L, R, you create a new heap consisting, new tree consisting of this only element, then you merge 2 of them together, then you merge the result with the third one. And you like got your structure back. And you may say like, okay, well, I assume that keys are values, but what are the priorities? Now there are multiple valid answers to this, one of which is like priorities or random numbers. Because random numbers guarantee this very high probability that mathematical expectation of the depth will be logarithmic. It won't be like strictly log n, but it will be like 2 log n with probability like 99.99999%. If you have up to 10 to the fifth nodes. So random priorities help to like balance the trip. And you can prove very easily that with given keys and priorities, there's only one trip that can exist. So yeah. So once you more or less understand how to split and merge, you may be interested like, okay, so I know how to insert, but how I actually query like range sum or range mean? I will answer like in the same way. You just split everything that's before L, have LR. I say like you split everything that's before L, you split everything that's after R. And this, if you not only store like subtree sizes, but also store minimum, and if once you update the minimum in like log nodes that got changed when you were splitting, then you will get minimum will be just here, sitting here for you. So yeah. So in this case, like actually these numbers keys are indices. The keys are not actually like in application for this problem. Keys are like this trip is not actually a BST over the key, right? It's BST over the index of the element. And key is actually like what is the value of the element. But you will see all the details much clearer in the implementation part. But main thing you have to remember about trips is that you can split them, you can merge them, and you can maintain a lot, and I mean a lot of statistics on the subtree in trips. Because of that, you can solve a lot of problems when you have to dynamically change your array and the length of your array. When length is variable, then you definitely need trips. And trips are not as complicated, I believe, as segment trees. Segment trees are also not always complicated now that I think about it, but neither of them is in STL. I believe some sort of trip is present in GCC, but it kind of fails like some performance tests. So it's like unofficial. I believe it's called, no, I won't say what exactly it's called because I may be wrong, but I think like it's called rope. If you Google ropes GCC, you may find some interesting information. But again, trips are pretty short to write, to implement, so you don't necessarily want to, you can write them yourself. And then you just have to think like what statistics I want to maintain. Is it subtree size? Is it minimum? Is it sum? You can maintain all of them, right? And unfortunately, I believe the trips have to be stored in form of pointers. So they are slower for problems when length does not change. So maybe when length is constant, you want to use segment tree exclusively. But if length is variables, then you definitely want to use trips. So that's it for the theory part, I believe. But if you have any questions regarding this lecture, I suppose You can always join my Discord server, ask me questions there, or you can, like, I don't actually like when people ask questions on Codeforces because messaging system on Codeforces is pretty badly organized. So I may lose some of my important talks in the heap of incoming messages. So I highly encourage you, if you have any questions remaining about it, to join my Discord server and just ask questions there. People are friendly, they will help you even when I'm offline. So yeah, if you have questions, definitely please join there. It's much more convenient than answering questions in YouTube comments. In YouTube comments, you still may very well ask questions, but more like organizational kind of stuff, like what will be the topic of next video or something like. I would like to see a video on that topic. If you have that kind of questions, then you can definitely ask them on YouTube. But if you have questions like, "Oh, my code is not working, please help," or what if we want to solve that kind of problem?" Then it will be much more convenient for both of us if you just join my Discord server and we'll talk about it. So yeah, I believe that's all I wanted to talk about Siri for today. So thank you very much for watching, and I'll see you like in 15 minutes with implementation video. I just want to prepare some stuff and prettify my code. So thanks for watching. See you soon.